Thank you for the introduction. So yeah, my name is Dusty. I'm a third-year PhD candidate at York University. And for those who might not know, York is located at the very north end, Toronto, Ontario, Canada. We're not the University of Toronto, but we're there and we're doing some cool research these days, I like to think. So yeah, like the introduction stated, I'm going to talk about our recently published paper in the Journal of Organic Chemistry on the synthesis of carbamoyl fluorides with a difluorophosgene surrogate. So I kind of have a sneak peek reaction scheme at the bottom of the title slide. You might notice carbamoyl fluoride moiety here. Kind of looks like an amide, except instead of your typical acyl functionality, you're replaced with just a simple fluorine atom. So looks like an amide, and you can probably guess that you can form an amide from such molecules, and you'd be right. So to get started, I want to talk about, here we go, amide utility and their typical preparation. So I feel like most chemists across all fields understand that the amide is an extremely important functional group that makes up peptides and which make up proteins, kind of your building blocks of all life. So those are extremely important. They're also heavily featured in the pharmaceutical industry. I have common pain relief drug lidocaine featured in the center of the screen. They're also heavily featured in materials chemistry. Here's a very common polymer, 1,6-nylon. It's an amide polymer heavily utilized in the clothing industry. So if you want to make an amide from scratch, typically you will use a carboxylic acid and an amine, and what people typically refer to as a peptide coupling reagent. So peptide coupling reagents are really handy. They operate by activating this oxygen of the carboxylic acid. So they bind to that, and then this makes the carbonyl carbon much more electrophilic. So your amine can then displace that oxygen, which is now attached to this extended leaving group of the peptide coupling reagent. These are tried and true reagents. There's a ton of them. They all are, there's tons of reviews that act as guidebooks to which one you should use. One drawback that people have found is that they have make the reaction suffer from a low atom economy. And atom economy is basically what percent of the atoms did you throw into the reaction are actually ending up in your desired. So since you have this now oxygenated leaving group here, and these reagents are typically pretty heavy, you now have a pretty low atom economy, which essentially means you have a high waste reaction. And because of this high waste, these reactions can be they're notoriously difficult to purify. Sometimes people might feel that's an exaggeration, but from reaction to reaction, you never really know. So a more atom economical route to access these amides is through a carbonylative cross-coupling. So you have a aryl halide, or your X equals iodide or bromide or chlorine or chloride, and a palladium catalyst to undergo the cross-coupling reaction. Under typical conditions, you would probably just get the aryl amine out of this reaction. However, these reactions are done under an atmosphere of carbon monoxide. Your first obvious drawback is that carbon monoxide is pretty toxic, and not something that most people want to work with, and it is often required to have high pressures of carbon monoxide. So these can be somewhat dangerous at times, despite their high atom economy. So if we analyze these two methods, there's kind of highlighted in purple, kind of the bond disconnection. So in the peptide coupling route, you are forming this carbon-nitrogen bond, where the carbonylative cross-coupling route, you're kind of forming both of these bonds around the carbon at the same time. So what's emerged in the last 10 years or so is a different bond disconnection of the carbon-carbon bond of the amide, which has been explored through the use of carbolide electrophiles. So most of this work has been done with carbamoyl chlorides, the molecule shown in the top left. These have been shown again and again to work well with palladium and nickel catalysts to form numerous amounts of very useful amide products. So your typical linear amides or your lactams or oxindals. as I've shown here. And the reaction mechanism is pretty similar to your average cross-coupling. So you have oxidative addition of your transition metal catalyst across your metal chloride or your carbon chloride bond. And you get this kind of oxidation complex that I've shown in the box. So while this is really well explored, you can read about it. The first reference I have at the bottom is a review by Chen, which really highlights a lot of these reactions super well. But more recently, people have taken to using carbamoyl chlorides for these types of reactions. The E group in 2020, this is, to the best of our knowledge, the first transition metal catalyzed reaction of a carbamoyl fluoride. So this gives access through a migratory insertion process and aerolation with the boronic acid of an aryl boronic acid to give these highly enantiomer-enriched lactam products, which are super useful to the pharmaceutical industry, and up to 96% enantiomer excess. So you might be wondering, what's really the difference? You're losing your halogen anyways, so why differentiate between the fluoride and the chloride? And I like to kind of use this example as when people ask me kind of why the carbamoyl fluorides are important, and you can make a number of arguments. There are some precedent for them being enzyme inhibitors and having some sorts of biological activity, but for me, I feel that these are most useful as simply another tool in a chemist's toolbox. So he demonstrates this by doing the same reaction with the carbamoyl chloride, wherein the product is obtained in only a 54% enantiomeric excess. So obviously there's some sort of halogen effect going on in the enantiomer-determining step of this reaction. And I would almost guarantee that they probably put this carbamoyl chloride through the ringer before they even thought of resorting to the fluoride. It's the only example that's actually in the paper, but that's likely the case considering until recently there weren't many great ways to make these compounds. Further interesting reactivity was discovered the following year by the Schoenebeck group, where you undergo this alkynylation of carbamoyl fluorides catalyzed by nickel. And the key to this reaction is the use of these silated alkynes. And this really drives the reaction forward thermodynamically, because when you do your transmetallation step, which is your alkyne binding to the metal and displacing fluoride, you're forming this incredibly strong silicon-fluorine bond. So these compounds could be used preferentially when you have a silated nucleophile, or vice versa. If you want to use the fluoride, you should use a silated nucleophile. And finally, just this year, the Chen lab demonstrated a kind of a spin-off of the E paper, where you have this diene tethered carbamoyl fluoride, which undergoes the similar reaction in high enantioselectivity. And again, I would assume that they started with the chloride. The Chen is a real champion of some of this carbamoyl chloride chemistry. They're the ones who wrote the review I mentioned earlier. So I think this is most valuable just as kind of a toolbox, or a tool in your toolbox. So why are there only 3 papers on this so far, if they're so useful? And the most obvious answer is probably just that they're kind of difficult to make. The original method, kind of this old school reaction, is reacting a secondary amine directly with difluorophosgene gas, which is pictured this very simple carbonyl compound. However, this is horribly, horribly toxic. It's not even commercially available anymore. And unlike the analogous phosgene, there is no common surrogate. However, some progress has been made in this front. Recently, the Zhang group utilized this trifluoromethyl triflate reagent, and this can give you carbamoyl fluorides from secondary amines in a very fast reaction, 2 minutes across the entire substrate scope. However, their reagent of interest is incredibly volatile, boiling point of 19 degrees Celsius. So that's kind of limits the use of this practicality-wise. This has to be stored in the freezer, obviously extracted, dispensed extremely fast to make sure you get quantitative transfer. This was further improved upon by the Schoenebeck group again, who obviously have an interest in these carbamoyl fluoride compounds as well, where they developed this relatively stable silver trifluoromethoxide solution. This also works well across a number of secondary amines. However, it's it needs to be prepared in a glove, so that also limits your practicality. It's light sensitive, and I believe you make this solution with 9 equivalents of silver fluoride to your trifosgene precursor. So that can be prohibitively expensive for small labs such as our own. And finally, just this year, Billard developed this organic trifluoromethoxide solid. This one I really like. It's seems much simpler than the other ones to prepare the carbamoyl fluorides through this method. And this is prepared in situ from the nucleophilic base dimethylaminopyridine with this trifluoromethoxy dinitrobenzene. All of these operate through a similar mechanism where you have your trifluoromethoxide anion, which eliminates fluoride to give you difluorophosgene in situ. So you get the same benefits of reactivity of this horribly toxic gas without actually having to handle it yourself. So our project, we gained inspiration upon reading this report from the JAP, where they trifluoromethoxylate alkyl halides. So they prepare, so they use this reagent, trilphosphonidifluoroacetate, or PDFA for short, and they designed this reagent to be a stable source of difluorocarbene. So upon gentle heating, this reaction decarboxylates and you lose triphenylphosphine to access the reactive difluorocarbene. And in this reaction, it's oxidized by this oxide to give you difluorophosgene in situ. And in a reverse to the other mechanisms, you actually add silver fluoride to get the trifluoromethoxide anion, which does the SIM2 reaction. So we thought that this seems like it could be a very good surrogate for creating carbamoyl fluorides. But before we got started, we took one more inspiration from the typical synthesis of carbamoyl chlorides. So this is done through the use of phosgene or a phosgene surrogate, such as trifosgene, which is kind of three phosgenes in a trench coat, if you will, a pyridine additive. So the pyridine additive acts to help decompose the surrogate as well as to activate the phosgene itself to make it more electrophilic. And then you have your amine displace a single chloride or the pyridinium that's now bound to the carbonyl to access the carbamoyl fluorides. And just for reference, this is how the cross-coupling papers I showed earlier prepare their carbamoyl fluorides, by just treating these carbamoyl chlorides with a nucleophilic fluoride source. It's still better than the original method with the difluorophosgene gas, but it's very steppy, especially considering those are some relatively complex amines to begin with. So we imagine if you take difluorocarbene and treat it with pyridine and oxide as an oxidant, you now have difluorophosgene and this pyridine act all in the same pot, and treating that with the amine should give you your desired carbamoyl fluoride with easy to handle reagents for in a relatively cost-effective manner. So with that, I took to screening an oxidant for this reaction with 1.5 equivalent Fa with this N-benzyl aniline, which is cheap and easy to track by NMR, so it's a really good choice to start. And right off the 93% yield with pyridine and oxide. We're pretty happy about this, but we wanted to explore the electronic effects of this oxidant. So if you add an electron withdrawing group, such as a cyano group at the 4 position, we see a pretty big decrease in yield. However, if you add a slightly donating substituent group, you get the quantitative yield of your carbamoyl fluoride. So this is really good, but we still want to explore it a bit more. And if we have a super electron donating group, like a methoxy group, we see a drop all the way down to 11%. So at the time, we weren't really sure what the reason for this was, but there's definitely a sweet spot you have to hit electronics wise. But keep that in mind, because I'll get back to that later. Specs, if you add a methyl group in the 2 position, you get pretty bad yield. If you add 2 methyl groups to the 2 and 6 positions, your reaction almost dies. Other oxidants, you see trialkylamine and oxides don't really work well at all. And you get some success with sulfoxide, similar to the Jow paper, with DMSO being the best oxidant at 2.5 equivalents. So after some equivalent screening that I'm on board, find that we can kind of just drop the equivalence of the 4-methylpyridine and oxide to 2.0. And we wanted to play around with some other difluorocarbons. Obviously, PDFA works really well, but we did screen a few others, and a couple that I want to highlight here are this potassium bromodifluoroacetate, which is actually, you make PDFA by treating this with triphenylphosphine. So if you're a medicinal chemist or someone who just wants to maybe try one reaction with a carbamoyl fluoride over the chloride or something, and you don't really want to commit to making all this PDFA, you can kind of stop here and still get your compound in hand. This difluoromethylene silocarboxylate sulfonyl fluoride compound also works really well with a sodium fluoride activator. However, it's a fuming liquid. It's pretty corrosive and honestly quite expensive, so we didn't bother using this compound further. So with that, we got into the substrate scope, and with the help of my amazing co-authors, we got a pretty broad scope of carbamoyl fluorides. We find if you alter the para position on the aniline, you maintain good yields. Your substituent is relatively electron donating. When you add electron withdrawing groups, you see a pretty big drop in the yield. Altering the nature of that benzyl group doesn't seem to have much of an effect. Adding ortho substituents, though, does seem to drop the yield a bit. If you have a orthomethyl group that blocks your nitrogen site, dropping your yield to 66%. However, an orthomethoxy only drops the yield to about 85%. So the electronics seem to outcompete the sterics in that case. Meta positions are tolerated well. This N-methylaniline works relatively well also, but we can scale that up to 1 gram where we actually see a slight increase in the yield consistently. Extended aromatics, bulky aromatics seem to drop the yield a little bit. This longer chain alkyl group is well tolerated. And maybe most excitingly, we see pyridine group, or these N-pyridyl carbamoyl fluorides can be synthesized in moderate yields. The drop in yield is likely due to both the electron withdrawing effects of the pyridine as well as nucleophilic competition with the pyridine nitrogen trapping difluorocarbene in the reaction. But we're very happy with these 2 compounds. Some more exciting substrates, we have a variety of alkene and alkyne tethered amines that work well, really well actually, considering that difluorocarbene can undergo 2+1 cycloadditions with these pi systems, typically giving you difluorocyclopropanes and cyclopropenes. Also tolerates a few more heterocycles and biologically relevant molecules such as this amino acid derivative, this piperazine and this cyclopropane. This tryptamine carbamoyl fluoride can be prepared in only 54% yield, and but we're also pretty impressed with reaction working in the presence of this H bond. And we do have a crystal structure of this compound which proves the carbamylation takes place at the secondary amine over the indole nitrogen. So I just wanted to kind of give a visualization of these reactions. In the left panel, we see the reaction at the beginning. PDFA is a really interesting reagent. It's not really in anything, but it does go into solution as you heat it and it decomposes into the difluorocarbene. So you can see it on the left as a homogeneous heterogeneous solution or mixture. And as it heats for a while, you see it go homogeneous. And then at the end, you get this dark solution on the right. So like any good organic chemist, we wanted to explore the mechanism. It seems fairly obvious that you're going through this difluorophosgene pathway, but you never really know. So set the reaction up in an NMR tube, and we sought to see if we could observe any reactive intermediate. So after 30 minutes, stuck this in the spectrometer, just wanted to get like a snapshot of, the midway point of the reaction. And by fluorine NMR, it's like kind of a mess. It's a lot of signals for a fluorine NMR. First of all, we can see the rotameric signals of the carbamoyl fluoride at about -20 and residual PDFA at -94. We're ready to kind of chalk these all up to out of random impurities because you see a lot of the same signals if you just see PDFA by itself. What did catch my eye, though, is at -40, this huge double coupling constant of 656 hertz. And you might be thinking, Dusty, that's not even a doublet. That's just two signals. That's too far apart. That's kind of what we're also, until you open up the phosphorus NMR spectrum and you see triphenylphosphine, you see PDFA overlapping with triphenylphosphine oxide. But if you look really close, you can see this triplet with a coupling constant of 656 hertz. So this is interesting. These are clearly two signals for the same compound, but we're still confused. Asked around the lab, everyone's confused. So we bring this to one of our department's phosphorus experts, Professor Chris Caputo, and he says, I think I recognize this. And he pulls out his PhD thesis and identifies this compound as this difluorophosphorine phosphorus 5 species. A recent paper by Tony characterized this compound in deuterated acetonitrile, so we actually can match our signals perfectly, and we're pretty sure this is what we have. We're still confused because how do you make this from N-oxides and amines and difluorocarbene? We hit the literature and we find this paper by Gupta and Shreve in 1984, where they take these phosphite compounds, react difluorophosgene gas, and this undergoes an addition and decarbonylative oxidation to get the phosphite analog compounds. So the same thing, but just these oxidants in between. I just want to mention these are really sketchy compounds. You can imagine an elimination of an alkyl group and a fluoride group here to get you to compounds that look a lot like the chemical weapon sarin. So we didn't really want to play around with reactivity further in these oxygenated compounds, but we did run a test of our reaction in the absence of an amine. We can see that this compound is formed in 44% yield. So this is pretty indicative of difluorophosgene being a big part of the reaction mechanism. And I included the phosphorus NMR of this reaction without amine, just so you can see this nice big phosphorus triplet. So one of my co-authors, Tristan, wanted to set out to find the intermediacy of the difluorocarbene. Because PDFA actually, the intermediacy of PDFA. So PDFA actually, upon loss of CO2 under heating, gives you this nucleophilic ylide, and then that's in equilibrium with this electrophilic carbene. So it's hard to a mechanism where the ylide is the predominant species, but no one has ever run these PDFA type reactions in acetonitrile. First, Tristan set out to see what happens if you just treat a carboxylic acid with PDFA, and it does undergo this carbene activity where you get OH to access these difluoromethyl esters. He then took it upon himself to treat this carboxylic acid with our optimized reaction conditions, and he sees 50% yield by fluorine NMR of an acyl fluoride. So this seems kind of weird, not what we were expecting, but again, we see this paper by Zhang, who you might remember from earlier, developed that trifluoromethyl triflate reagent, and he has a whole paper on converting carboxylic acids to acyl fluorides. And this is again operating through a mechanism involving difluorophosgene, where you create this mixed fluoroanhydride, and the excess fluoride decomposes this into the acyl fluoride. So again, more proof that we are operating under this mechanism where we produce difluorophosgene in situ. So I take you to the final mechanistic proposal. We obviously decarboxylate PDFA under thermal conditions to the Ilide, which is in equilibrium with difluorocarbene. Similar to the Zhao reaction with the sulfoxides, the pyridine and oxide attack the carbene to get this zwitterionic adduct. This collapses into difluorophosgene and your 4-methylpyridine. And this is where I want to talk to you about potential side reactions. So some of these reactive intermediates can potentially form adducts with the pyridine oxide, as it's a very nucleophilic species. And we suggest that it's likely with the Ilide and difluorophosgene forming these interesting zwitterionic compounds. The compound on the left, we assume, is collapsing to give triphenylphosphine oxide and more difluorocarbene, which is where the trace amounts in our spectra are coming from. So if you remember, our 4-methoxypyridine and oxide work really poorly. So we are suggesting that when your N-oxide is too nucleophilic, it drives the equilibrium to the outside of these reaction schemes, and thus slowing down the actual reaction. And of course, you have your reaction with triphenylphosphine, we observed by NMR, and your reaction of interest, your pyridine-mediated carbamoylation of your secondary amine to access these fluoride compounds. So with that, I'd like to conclude that we've developed this really unique difluorophosgene surrogate reactor where we can access carbamoyl fluorides of a broad substrate scope. And we have some mechanistic studies which show that this does go through an a difluorophosgene mechanism, and difluorocarbene is the reactive species that is utilized from the PDFA decomposition. And we really like this method. We've tried a lot of the other methods in our lab, and so far this is kind of the most practical one. It's very easy to do, very simple, easy to make the precursors, and most of the materials are commercially available. So with that, I just want to say, this was the first paper out of our group, and it's been really exciting publishing that. And I promise that there are applications of these carbamoyl fluorides coming, hopefully some very soon. But yeah, I just kind of leave that open-ended and let you know we are more plans for these molecules. And finally, the most important slide, the acknowledgements. I want to acknowledge my co-authors, Tristan and George. Tristan just graduated with his Master of Science degree and is currently on the job market. George is still an undergrad here at York University. And then, of course, Professor Meekins for organizing this seminar series. I'm really looking forward to your questions and everything. The Lee Group, our PI, Christine Lee, amazing working with her and all of my fellow graduate students and the talented undergrads that we've had joined the group. Our NMR technician, a graduate student in our group, Jesse LeBlanc, who solved that X-ray structure for me. Chris Caputo for helping identify that phosphorus 5 pound. Of course, my funding sources and the lab's funding sources. Grateful for that financial relief as well. And if you have any further questions beyond the question period, if you maybe don't like asking questions online, I've put my email at the bottom here, and feel free to contact me afterwards. Love to answer anything about the project or the lab or Toronto in general, whatever you want. So yeah, thanks for that. I guess it's a question time.
Fantastic talk. That's super cool work, and I actually was able to follow it, so that's good. All right. So yeah, you do have a good number of questions, so we'll go ahead and just jump straight into it. The first one here is this was back from the beginning. Are the yields the same for the Yi, carbamoyl, chloride, and fluoride examples?
Or something. So the yield is actually, I don't remember the yields exactly. I just kind of wanted to highlight the selectivity in this example, but the yields are definitely lower for the as well.
Okay.
And that's not super well understood, but there is numerous observations observations, collagen-dependent reactivity and selectivity in these types of cross-coupling reactions.
Okay. Let's see. Can carbamoyl fluorides be used with something that doesn't form a strong EF bond? In the example, or in parentheses here, assuming boronic acids form BF bonds like the silicon fluoride bond from the alkyne example.
So there is, cross-coupling wise, there's not really any examples outside of the boronic acids and the silicone and silated compounds. It definitely, you can definitely displace them with like a strong nucleophile. The Schoenebeck group has a paper from the 2 years before this in Nature, actually, where they make a bunch of these CF3 carbamoyl fluorides, which are obviously a bit more electron deficient than the typical carbamoyl fluorides, and those nucleophilic displacement with Grignard reagents, amines, alcohols, thiols. I think the non-perfluoroalkyl carbamoyl fluorides are a bit tougher, actually. We tried a couple. We wanted to kind of include a few example papers, but the straight up like alkyl, electron-rich alkyl carbamoyl fluorides were kind of difficult to get reactivity in.
Okay. All right. Let's see. So, okay, here we go. So this, are there any issues with unreacted difluorophosgene from the stable generators of it?
Some of the methods you could, no one has any explicit warnings of etching or anything. We included a warning in ours where we just say, so these are all room temperatures, the only one with difluorophosgene that you actually heat. So we just kind of put a safety warning noting that you should let the reaction cool completely and vent in your fume hood before you do anything else with it.
Okay.
So toxicity, I'd say, is kind of an issue. You want to just follow your standard lab safety, but I think the pyridine mops up any hazardous byproducts pretty well.
Okay.
I've never seen chink on scale up.
Okay, so it's not as big as using the actual gases, but you still take the precautions just in case.
Yeah, because there is an excess, but obviously with most of these yields being pretty good, you're consuming most of it. Yeah. So like if your standard reaction, you have 97% yield, you have 53% phosgene laying or difluorophosgene laying around potentially. So you just want to make sure you vent it carefully.
Okay. Yeah, that makes sense. Let's see. Can you do this chemistry in non-coordinating solvents, like, for instance, toluene?
So that's an interesting question. Most solvents work fairly well. I didn't in solvent screen. I don't think I made the supplementary slide, but in our screening, toluene actually also gave full like quantitative yield of our model substrate.
Okay.
We just chose acetonitrile here to get rid of, but we're finding as we kind of scale these up to do more chemistry that sometimes you run into a bad reaction, you go, oh darn, you have to try toluene instead. And then sometimes you find that works better.
Okay, I got you. Let's see. This one did nitrous oxide work?
As an oxidant?
I think that's what they're asking, yeah.
We didn't try nitrous oxide.
Okay.
Just the purity, just the amine and oxides and the sulfoxides.
Okay.
It's an interesting thought, though, because I've seen some cool chemistry with nitrous oxide recently.
There you go. Maybe that'll be the next paper.
Be an easier cleanup for sure.
Absolutely. Let's see. What kind of purification or workup, I guess, or workup are you using before running NMR?
So in the reactions, I would just let these vent, and then I just directly rotavap them down or transfer them into a solution of my standard, rotovap them down, and then dissolve them in deuterated chloroform. But in the actual substrate scope, we found that there is quite a few byproducts of the reaction. So it's like you end up with a lot of material for the scale of the reaction. So we found the best way is to work these up and purify them is to just, once your reaction is cool and vented, you just transfer to a flask, add the correct amount of silica gel, and you rotovap that down directly, and then you dry load that right onto your column. We find, because these are actually not very polar, the carbamoyl fluoride kind of kills all the polarity that you have from a typical amine or amide derivative. So we're finding that if you try to like dissolve these to add, you need a much more polar system to dissolve them. You're actually running your chromatography in. So we found a lot, even though they're looked on TLC to be really good separation between your product and phenylphosphine, they would be co-eluting just because you had to use so much solvent to get these things in. So yeah, the best way we found is to directly dry load the reaction onto gel.
Okay. Let's see. This next question is: do you make the PDFA or do you buy it?
So I don't think there's a commercial source of PDFA in Canada, anyways. But we do make it. It's pretty straightforward, actually. I can find the slide. So yeah, if you start with this ester, we can buy a pretty sizable jug for a pretty good price from TCI, and simply saponify it with KOH. That's the overnight reaction. That's what the Zhao group listed. I'm not convinced it actually takes that long, but there's not really a great way to monitor that. So we just run it overnight, rotovap it down, take that the solid of that reaction directly, dissolve that directly in DMF, add triphenylphosphine, leave it overnight again. Like I said, it's not really soluble in anything to the point where you leave this reaction stirring in DMF, and then you come back in the morning and it's all precipitated out of the DMF, and you just filter it and wash it a few times. So we do make it, and it's a pretty simple process.
Okay, good deal. And our last question here is asking again about the oxidants. Have you thought of using something like nitrosobenzene?
Nitrosobenzene. No. Again, yeah, all the oxidants we tried, I kind of listed in the presentation. Another good idea. But yeah, we kind of went in thinking about the pyridine and oxide. So kind of started with, I mean, you obviously tell a more coherent story in your presentations and stuff, but we definitely started with just pyridine and oxides and the sulfoxide. Sulfoxides are known, and we thought of the pyridine being a good activator. So that was kind of our focus going in. We didn't really get, and obviously we didn't get anywhere too exotic. Those yields came up pretty fast.
Yeah, let's say it sounds like you got the right one right from the start. That's always nice. All right, well, very good. So I think that's all the questions we have. If anybody wants to get any last minute ones in, while we're wrapping up, please feel free. But thank you again to Dusty for a really interesting talk. The chap thoroughly enjoyed the story that you told there. So thank you again for sharing that with us. It's really cool work. Appreciate you showing it off to us.
Oh, well, thank you for the invite.
Yeah, absolutely.
It's been fun. It's needed a brush up on presenting. It's been a little while.
I'm glad you could do that. So thank you again to everybody for coming out. We will be back next week with another talk. So please join us again, same time, same place. And hope to see you out next week. If you were new this week, feel free to come out as well. And make sure if you follow the stream, there's a follow button right to the bottom right of the stream window. If you click on that, you'll get a notification. The stream does go live. Again, please feel free to join the Discord. Everybody's welcome to join that as well. And with that, I will say thank you one more time, and have a great weekend, everybody.
Thanks a lot.